Hello everyone, my name is Wonyeong from Yonsei University. Today I will present our research LEAP, a layer-wise energy adaptive framework for multi-DNN real-time intermittent system. I worked on this with Hyunwoo from Sungkyunkwan University and my advisor Jinkyu from Yonsei University. Recently, learning deep neural network on battery-less device has become popular. Now, I will share how we guarantee real-time performance for multiple DNN in this environment. Intermittent systems collect energy from sunlight or vibration. They are used for wildlife or health monitoring. This system uses multiple DNN models to analyze multiple data. The most important thing is finishing tasks on time. If the result is late, it is useless. For example, if an animal leaves the camera before the analysis is finished, the data has no value. Our main goal is to guarantee real-time execution for multiple DNN tasks and maximize accuracy. But we have two constraints. First, the energy supply is unstable, so tasks stop often. Second, microcontroller or MCU have very limited memory. Existing methods cannot solve both problems at the same time. Let's break down the challenge. Under a continuous power supply, tasks are completed well before their deadlines. In an intermittent environment, the device must periodically pause to harvest energy. This necessary downtime often causes tasks to exceed their deadlines. As you can see, ultra-low power MCU have extremely limited on-chip memory. When we load the first and second DNN models, the available SRAM and FRAM quickly fill up. Now look at the third model. Because of the cumulative weight and storage cost, there simply isn't enough space left. As a result, multiple DNN cannot coexist on the device at the same time. To solve this, we ask three questions. First, how to design a DNN and training that supports multiple latency accuracy trade-off with minimal memory. Second, how to characterize intermittent inference and integrate it into real-time frameworks. Third, how can we combine Q1 and Q2 to meet deadlines of all tasks and maximize accuracy? There are two common existing solutions. The first is static pruning. It makes the model smaller, but it cannot adapt to changing energy. The second is the multi-exit approach. It adapts well to energy changes, but it uses too much extra memory for the MCU. Here is the overview of our framework. We train the model to dynamically change its width. Then, our framework dynamically controls the width at each layer based on available time and energy. This guarantees real-time execution and maximize accuracy. Now let's look at the component of our framework that address Q1, specifically to overcome the memory limit we discussed. Our first solution is the LEAP model. We designed it to dynamically adjust its width layer by layer without needing any extra weight, which is key for saving memory. To keep the performance stable even at smaller widths, we use a teacher model during the training process. As you can see in the loss function, we minimize the distance between the teacher's feature and LEAP's feature. Now let's look at the training process in detail. We train the model in multiple stages, starting from the narrowest width. At each stage, we perform channel reordering based on L1 norm. The idea is simple. We identify the most important channels and move them to the front. By repeating this reordering up to the full width, we ensure that even a very thin version of the model still contains the most critical information for accuracy. As we can see in this graph, LEAP provides much more trade-off points than multi-exit models. While multi-exit only has a few fixed exits, LEAP offers a wide range of options, allowing the system to reach much more flexibly to unstable energy environment. LEAP achieves this flexibility with almost no extra memory. While multi-exit model needs significantly more memory for each exit, LEAP stays almost as light as a simple base model. Now let's address Q2. Our second key idea is the energy-aware time budget. To handle unpredictable energy, we first analyze the energy harvesting cycles for each task. To find a reliable upper bound for completion time, we look at the worst-case energy scenario. First, Hmax is the maximum time needed to harvest energy when the charging rate is at its lowest. Once the device turns on, epsilon minimum provides the minimum execution time guaranteed, assuming the highest power consumption. By combining this longest harvesting delay with the shortest execution window, we turn unpredictable energy into a stable time budget. This allows our scheduler to ensure all tasks met their deadlines even under the most difficult energy conditions. Based on the result of Q1 and Q2, we will now show how Q3 achieves real-time execution and maximize accuracy. Finally, we combine the model and the time analysis for runtime scheduling. When a task is first executed, the scheduler selects it according to fixed priority rule. Every time the power comes back on, the system re-evaluates the remaining time before the deadline. Based on this, it reselects the best width for only the remaining layers to meet the timing constraint. This process ensures that we always meet the deadline while maximizing the overall accuracy. We test our framework on real hardware as shown in the figure. We set our parameters based on real power cycle measurement. Now, let's look at the real-world result. LEAP successfully met 100% of the deadlines for all tasks. In terms of accuracy, it showed an improvement of up to 10% compared to traditional fixed models. While multi-exit model failed to execute due to memory constraints, LEAP operated reliably within the limited resource. The simulation result showed the same trend. LEAP had zero deadline miss for all tasks, ensuring 100% reliability. This confirms that our framework effectively handles real-time constraint in simulation as well as in real-world environment. In simple two-task case, multi-exit model can be slightly more accurate because they process all features up to their exit. However, as the workload increases to 3 or 4 tasks, multi-exit model completely fails due to the memory overflow. In contrast, LEAP maintains zero deadline miss and achieves higher accuracy than static models in this complex scenario. To wrap up, I would like to summarize the key contribution of our work. First, we built a memory-efficient architecture, enabling layer-wise adjustment with almost no extra memory. Second, our energy-to-time abstraction turns unpredictable harvesting into a stable time budget for real-time guarantees. Finally, we have proven reliability, achieving 100% deadline satisfaction even when multi-exit model failed. Thank you for listening.